Oh, it's okay. I think he will talk after the session. Mr. Sai, you can take your session.
All right. So thanks, Dr. Satish.
My
Thank you,
colleague
sir.
also available. Dr. B. Shinals also is joined for this meeting. I welcome you, sir.
That- All right. So let me share my screen and let me know once you see it. So are you guys able to view my screen now? Are we good to go? I think yes, I see that it is being shared. So all right. So what we are going to look at today is basically general distributed systems and microservices in specific. And the aim of whatever I'm going to talk in the next probably half an hour, 45 minutes is going to be give you all a high level introduction of what distributed systems are, and in specific what microservices are all about. And towards the end of the talk, I hope you guys will walk away with enough understanding to decide if you're already doing some software development, to decide if microservices are what you would want to do, or also if you're a budding software developer, how microservices could help, in what sort of scenarios you could start using microservices and explore microservices further. So with that agenda being set, I think we can just get on with what microservices are all about. Okay, and what are we basically going to look at as a part of this entire talk? So we'll try and understand what distributed system actually means. So we'll try to understand the concept of distributed systems, and further we'll see what microservices are. So are distributed systems and microservices the same, or how do they differ? And now a precursor to microservices was service-oriented architecture. So if you look at uh, the field of software development, right? So software development has evolved over a period of time, and as and when it evolves, a certain new paradigm of programming, a paradigm of design actually comes to the picture, and that takes over. And currently, it's the trend of microservices and building applications in microservices fashion that is being preferred. And microservices are stemming out from distributed systems. That's the underlying concept or area of programming. And distributed computing is again something that we achieve using distributed systems. So, and then further we'll see what makes basically microservices, because these are all architectural patterns, right? So what characteristics we have, and anything that is coming up will come with its own baggage, will come with its own set of challenges, and we'll be looking at what challenges we have generally with microservices, and the way anything evolves, right? So we have certain patterns and principles which will emerge over a period of time, and we are going to look at what sort of principles and patterns that have emerged with microservices. And then, like I said, as a software developer, or as a software enthusiast, where are you going to start off with microservices? And then we'll see how we are leveraging or moving towards microservices and using microservices at Frequent. That is where I work. I work as a senior software engineer at Frequent. So Frequent basically is data and analytics and insights provider to the alternative assets community. So, and then we'll wrap up with basically any sort of questions or anything that you guys would want to understand for. Okay, so with that platform being said, so now let us understand what is a distributed system. So this specific definition, right? So whatever you're looking at, so I'll give you probably a couple of seconds to go through it. So this is basically how Wikipedia defines what a distributed system is. So if we try to break it down further, the key things is it's like different components or different software entities communicating with each other over a network. So you could probably have one part of the software deployed on one machine and another part of the software deployed on another machine. So these two machines are connected over a network. And now an end user who is using the system will use the system as if he's talking to one single server. But behind the screen, there are multiple components running on multiple network or machines which are connected over a network, and they are talking with each other in order to deliver whatever functionality or the feature that the user is looking at. Right. So that is how I mean Wikipedia, like defines what a distributed machine or distributed system is, right? So in a real world perspective, right, so are there any distributed systems or is it just theoretical computer science? But if we look at it, there are many real world distributed systems that we use day in and day out without actually knowing that it is a distributed system in itself. For example, if you look at internet, right, so internet itself is a distributed infrastructure. There is no one single centralized machine. There is, for example, Google. If you take the Google search engine, right, so your request that is going from your machine would be served by some server sitting in, say, Bombay, or some server sitting in a location which is closest to your geography. But does that mean that, okay, the software which is running on a server in Bombay is different from a software which is running on a machine in California? No, these are all connected over a network. These are all orchestrated together. These all work together. So this is what actually makes a distributed system. But as an end user, do you know, like, which server you're talking to? It doesn't matter, correct? So at the end of the day, whatever you require, you would just enter a request and that gets served. So that is basically the beauty of distributed systems. And again, they come with a lot of cost and a lot of steep learning curve, but we'll see, like, what distributed systems are all about. So now moving forward, so what sort of like advantages we get and what sort of challenges we get when using distributed systems. I would not go into the depths of it because, as they say, for somebody who is like just starting off, the devil is in the details. So I'll try to keep it as simple as possible so that not to, like, intimidate with a lot of technical jargon and all that. But we'll try to keep it as simple as possible, and at the same time, like, getting you guys to understand uh, what uh, what the fundamental concepts are, right? So there are basically three primary advantages of distributed systems that I would want to highlight. So first thing is like horizontal scalability, right? So when you're talking of horizontal scalability, let us take a very simple example wherein if you're running your own laptop, right? So a laptop is also a computer, and also the server on which the softwares run, they're also a simple computers. So they have a processor, they would have some RAM, and they would have some hard drive, and they would be running, right? So now consider that you're using a 4 GB, a machine with 4 GB RAM and with some processor, right? So there would be certain limit to which it could run applications, or it could perform any operation, right? If you're trying to run a really, really heavy software on a machine with 1 GB RAM, your performance would go down. Right. So similar is the case with software and software development and the infrastructure as well. So your software is deployed on servers, and that is where your end users will consume your software, right? So there would always be certain limitations with respect to how much capabilities that your application could deliver, how many users that your application could serve, right? So from that perspective, so there would be limitations on that end, and what we do is add more machines to it, and that is what we call horizontal scalability. So now if I can serve, say, 100 users with one server, if I add two servers, I can serve 200 users. And if I had, like, more servers as in when I need, I'll be able to cater to more number of users. I'll be able to serve more amount of traffic. So that is what horizontal scalability is all about, right? And when we are talking of reliability, right? So reliability is something that is inherent, right? So for example, say you would always take it for granted that whenever you search for some specific thing in on Google, so you would always get a response, right? So is it always a case that Google will work without failing? Probably not, they will have some sort of reliability mechanisms or fault tolerance mechanisms which are in place and which are responsible for increasing the reliability of the system, so that every time you try and search for something or perform some operation, you would always expect that operation to go through, to succeed. Okay. And when I was talking of performance, I think horizontal scalability and performance would actually go together, right? So you would have now you would have more computation power because a lot of machines are connected across the network and doing the same job. I'm parallelizing everything. I'm distributing the computation, right? So this is where distributed computing actually shines, right? So in this way, I'll be able to improve the performance of whatever I'm doing. So these are the advantages. But now when we talk of challenges, what is it that actually makes distributed systems a little challenging? Right. So one thing is scheduling. So when I say scheduling, when you're talking of multiple machines that are happening, when we are talking of distributed computing, we are sort of parallelizing everything. Everything would run independent of one another. So assume that you have spun up 3 or 4 machines, 3 or 4 servers that are actually doing your job, right? So each of the machine is responsible for its own stuff. So it would do its job and then it's done. Now, when multiple things are of these nature are running in parallel, you would not have any control over which part of the activity should run after which part. So that kind of scheduling that we are looking at, that is not something that is inherent in distributed computing, and that is where priority comes. So when we say priority, okay, first this job has to finish, and then another, and then another. So that prioritization actually comes, and the scheduling is not something that is not that is feasible. But prioritization, yes, we can do prioritization, but achieving prioritization also is a challenging task in itself. So that is one challenge we see. And the second thing is latency. Now, when I'm talking of distributed computing, the first thing that I mentioned is there are multiple machines which are connected across a network, and each of them are talking to each other over the network. So if you understand the underlying infrastructure of any network, so you would have a transport layer, right? So this transport layer, you would send packets of information and they go over a network. So since everything is a network call for organizing or synchronizing anything, that is where latency comes into the picture. All right. And the third thing and the most crucial thing is, again, performance monitoring and observability. To put it in very simple terms, you should be able to see at any point in time what your application is doing. So that is that is one of the fundamental tenets of software development. So we call it observability, right? So if you do not know what your software is doing at any point in time, you will not have enough control over what could happen. So if something could go wrong, you will be able to see the metrics that you have, and you will be able to tell, okay, there is a possibility that this failure could occur, or there is a possibility that something like this could happen. So in order to have that kind of a view, you need to have some sort of uh, processes in place, and generally we call them as tracing across distributed systems, or there are several things basically which actually come into the picture. So since everything is distributed now, network failures, and I mean, it's not just the application itself malfunctioning, it could also be some network failure or some networks which has gone down when in a data center, or there is a power failure in the data center. It's not like one single thing. So to keep a track of all of this, you should have robust infrastructure to maintain all of the observability metrics. So that is one other challenge. So these basically, at a very high level, the advantages that we could get as a result of distributed computing, and also what makes distributed computing a really tough thing to actually pursue and implement, right? So now this is actually a really beautiful thing, and this is something that we or any software developer who's starting with distributed computing should take a look at, right? So what these basically are, these are the policies of distributed computing. These are the myths of distributed computing. So what do I mean by that is, so these are the set of things which every naive or a beginner software developer would assume, but which are not actually true. Okay, so the first thing, I mean, these are almost all of them are self-explanatory except for a few, right? So we'll like quickly run through these, and then I will probably stress a little more on those which are not exactly straightforward. Okay, so the first thing that, like, an assumption that every software developer makes but is not true is that the network is reliable. So if you remember the previous point that I was talking of, where we are saying that, okay, the network that we are actually using is reliable, but that's not the case, right? There could be power failures, like I said. There could be a faulty network equipment, network switch, which could take your machine out of the network altogether, right? So there are too many things that are out of our control and which could fail, and outside of the boundaries of your application or the software that you have written. So that is what the first policy is all about. And the second thing is latency. So the first and the second, I think they go hand in hand, right? So now that we are bringing network into the picture and we are like talking over a network, there would be some cost, some latency that is induced, because you have to actually send some data across these nodes which are in the network, right? So latency is one factor which is a direct repercussion of the presence of network itself, right? And the third thing is, this is also very straightforward. Bandwidth is infinite. So to give you a context of when these were actually put up, is like almost 15 years ago, right? So almost 15, 20 years ago, there is this guy, Peter Dutch, who has actually come up with these policies of distributed computing. And the last one that you see is actually I mean, he came up with 7 of these, and the last one is actually added by James Gosling, who is the architect of Java at Sun Microsystems. So he is the one who has added the last policy there, that the network is homogeneous. Now coming back to the bandwidth thing, so that is of all these policies that you're seeing here, bandwidth is the only thing which has been improving over a period of time. Now we have almost like, because my internet speed here, if you see, that's like 100 Mbps with constant connection, right? So if you look at really big data centers and data infrastructures, you would have like 1 Gbps throughputs across the networks. So bandwidth is the only area which has improved over a period of time. But the thing that we need to consider is, like, bandwidth is always finite. It is always limited. So we should always, so what that actually means is that we should have, we should always consider that the bandwidth is infinite and just, finite, and just send only that amount of information across network. Do not send a lot of data across the network, because that would in turn improve or increase your latency. So, and then the fourth thing is network is secure. Is the network secure? That would be far from reality. So networks are always assumed to be totally unsecure, and we should always consider the security implications, and we should always consider security as one of the fundamental things as a part of the design of the software itself. We should cater for security and should not consider that the network is secure. And topology, so the way in which your network is currently existing, so the physical structure of your network is basically the topology, right? So you could have more and more machines that are being added to your network. Your network, like, star topology, ring topology, we have multiple topologies. So those are out of our control. So there is always a good chance that somebody could introduce a new node into your network or remove an existing node from the network. So the topology will always change. And the people who actually manage the hardware infrastructure, so these days everything is cloud native. So you have AWS. So there is no actually a system administrator who's sitting in a data center and sort of uh, managing your data or infrastructure. Correct. So Yes, so we have to also factor in these kind of things. And when we say transport cost is zero, so this is something that I would want to stress on. So this could be interpreted in two ways. So first thing is whatever we send across the network, right? So say you are sending an email, but what actually travels over the network is bits. It's all ones and zeros, right? So there would be an inherent cost when I mean that is incurred when we actually convert, or like we in software terminology we call this marshalling, right? So from whatever format you have, you're converting that to bits and pieces, or bits, ones and zeros, that are actually understood by a computer. So we call it as marshalling. So the cost that is incurred as a part of the marshalling, that is never considered, but that has to be considered in the case of a distributed system. And the second way that we could interpret is that uh, basically what do we say, the cost that is incurred to run the network itself, right? So we are building a network, correct? So in order to keep the network up and running, there would be some cost that is incurred. So these two are the different interpretations that we could have for transport cost. But at the end of the day, yes, these are actually non-zero in reality, and have to be kept in mind while building distributed systems and working with distributed computing. And last and final thing is homogeneous network. Now even on this specific call, some of you might have connected using your mobile devices. I have connected using my laptop. Somebody might have connected using an iPad, right? So there are now different kinds of machines that have connected to the network. Basically here the network is nothing but your internet, because that is the common network that we are on, right? So now you're using different sorts of devices and different sorts of medium in order to connect to the network. So this is what actually it means. Your network is homogeneous, and it is, you should never assume that okay, the user will be using only a specific kind of a medium to connect to the network and then consume your application. Now given that these, there are like so many things underlying, even from an infrastructure standpoint, and just from the implementation standpoint, and from a perspective of actually understanding distributed systems are generally hard. So in fact, anything that comes with the word distributed becomes inherently harder, because there are too many things that are coming up, and too many moving parts would actually come into the picture, and that is what makes it harder, right? So now, before starting off with microservices, I think most of you guys, or most of you people, have worked with one or the other, at least a small software application, right? So it could be as simple as a website that is probably fetching some data from a database and then writing something back to the database, right? So if we consider any of those kind of applications, a typical application would be, I mean, the code that you write, I mean, be it PHP that you have used, or be it anything else, right? So whatever you might have used at any point in time, at the end of the day, you will have to write some code. Now, this code always will reside in one folder, where you might follow some convention, some structure, right? So that is what we actually call a monolith. So monolith is a kind of an application where all your entire code, we call it code base generally. So that code base is all residing in one single place, right? And we also have another kind of application where this monolith itself is layered, right? So what do I mean by layering is, if you are considering a web application, right? So that web, the presentation layer is what we call the topmost layer, the UI, user interface that you're seeing is the presentation layer. And then you would have some business logic. There has to be some logic behind what kind of data you would want to fetch and what kind of data you would want to actually update into your databases. So that is your business logic. And then you would have a data access layer, which is actually responsible for reading and writing from your data sources. So now if you see, there are three different layers here. So there could be any number of layers based on the application that you're building. But those kind of systems are called layered systems. So these are the kind of the applications that these are the kinds of architecture, software architectures that were being used earlier, right? So again, this had actually worked for a really long time, because microservices had come into the picture only during the early 2010. So like 2012, 2013, 2014 is when microservices have actually gained a lot of traction, right? But even before, there was software development that was existing, and a lot of applications, in fact, really good applications have been built way before 2010. Correct. So what are those what are those areas where these monoliths and layered systems, that is the world before microservices, so what are the different areas where they shine, and what are the challenges that people were having as a result of which they moved, or they are exploring microservices. So we are going to take a look at these things. So we'll first look at what sort of benefits we get out of the monoliths and the layered systems. And one basic thing is one single code base. So like I said, all your code will probably sit in one directory with whatever directory structure you are maintaining, and there will be one technology stack, right? So your entire code base might be written in PHP, or your entire code base might be written in JavaScript, or your entire code base might be written in any language for that matter, right? But there will be only one single technology that you would be using. Probably you might use MySQL as your database, or you might be using Oracle or SQL Server or whatever, right? So there will be always one single database technology, one single backend technology, and one single front-end technology. So if you look at it that way, there is only one technology stack that you use for each of these purposes, right? And the other advantage we get is everything is located in one single place. Everything is homogeneous, and there is no lot of there is no cognitive complexity, or maybe I can put it this way: the cognitive complexity is way lesser, right? So it is easier to have a clear picture of what your application does, which part of your code is responsible for which kind of activities that it's performing. And the other thing is, when you want to scale the application, say for example, your application is currently able to handle only 10 users, so you want your application to be able to handle say 50 users. So scaling that, so that is what we call as scaling. So scaling that in the case of monoliths and everything, or layered systems, is way easier than a distributed system, right? And also you must be aware of this debugging process. So if you ever write code, so in very less scenarios, it might so happen that whatever code you have written would have gone through successfully, compiled successfully, and executed successfully. But in most cases, we might be hitting few compilation errors, or we might be hitting few logical errors. And we what we end up doing is, if you're writing some C code or something, we insert some print statements to see what exactly is happening. Or if you're using some object-oriented programming language like Java or C Sharp, you have a debugger, you have an IDE where you write code, you debug. So this process of actually debugging and then trying to fix any sort of discrepancies that you're seeing is much easier when you're actually building monoliths, when your system is built like a monolith and behaves like a monolith, right? So if everything is rosy, why do we actually want to move away from something that is working fine? So that is where the challenges actually could come into the picture. Now assume that for small applications, yes, it works really well. But consider a real world scenario where you have built a product and users are using the product, and you would want to keep evolving your product. You would want to keep adding new features to your product. That is where things actually get tricky. So if you want to add a new feature, so generally what happens in real world software development is you keep adding more and more code to your existing code base. The more code you add to your application, the more complicated things would get down the line, because whatever decision you might have taken at a previous point in time, that might become a bottleneck for you in order to build something in the future. So there would be a lot of dependencies, and every single decision that you make over a period of time, along the life cycle of the product, would become critical. So that is what I mean when I say that your code base could get unmanageable. And since you're going to have these kind of blockers, the rate at which you can build new features and deliver new features, that would go down. And get around this, you would probably build a lot of code which is tightly coupled. When I say tightly coupled, it becomes the code that is like difficult to be changed in the future is something that is called that is tightly coupled. And the rate at which you're delivering something. So we generally have things called release cycles. So the release cycles are the other thing, and the release cycles could go down, right? And since we are hitting all these limitations, we would eventually hit a specific limitation where your application will not be able to handle huge amounts of loads. So that is where the problem with scaling actually comes into the picture. So that is basically the the world before microservices, and why we actually want to move ahead and move away from the existing things, right? So now let us move even further. So what microservices are? So earlier I was talking of systems where everything is inside one single directory, right? Your code directory. Now and every single feature is being served from that entire code base itself, right? So now microservices, like I said, is just an architectural style. It is just a different way in which you build your applications. And the thing which actually makes up a microservices, or a microservices style of building things, is that we do not have one huge code base, one huge application. Rather, we would try and break this application into very, very small pieces which are going to work with each other. Now, if you try and relate it to what distributed computing and what distributed systems I've spoken of, you would be able to draw some parallels. So there also you have multiple components which are running independent of each other. And here also we are breaking the entire application down into small services which could function autonomously within themselves, right? So that is basically what a small suite of services means, right? And each service will actually run in its own process. And from a computer science perspective, you have processes and all these kind of things, right? So that is basically the it's just a computer process. So each of your service that we are building, I'll come back to what service actually means, but just whatever services or whatever components that we are building, they would be running in their own processes, and each of them would be communicating with using some lightweight mechanism. In this case, HTTP. So HTTP is the hypertext transfer protocol. So it's the transfer protocol which is responsible for the transfer of information. And using HTTP, these components that you're building, they talk to each other and they try to do a job collectively, right? And building around business capabilities is something that is going to make sense like the more I describe microservices and the more we talk about that. Okay, so and independently deployable. Like I said, each of these components, they have to be deployed somewhere on some server which are running, right? So they have to be built in such a way that if I am having 4 different components which are serving as one application, I should be able to deploy any of these components at any point in time without having an impact on the other 3. Okay, so that is what being independently deployable means, and have minimum centralized management of services. So what what sort of management are we looking at, right? So when you talk of management, if you remember, I spoke of the case where we were talking of observability, right? So we could have some sort of logging, or uh, consider the use case of actually interacting with the database itself, right? So how it has to talk to the database, it should not be governed by some centralized authority. Every service or every component should be able to make a decision for itself about how it wants to deal with different aspects of the functionality. So that is where this concept of not having, or having as less centralized management as possible, comes into the picture. And one other beautiful thing, or one other beautiful flexibility which microservices actually give, is you can build each of these components in different languages that you want. So what that means is that in the earlier world where we had monoliths, you are stuck with one single language. If you want to move or to a different language, say for example you've built something using PHP, and now you would want to move to something like Java, or say JavaScript, because you could write both front end and back end with JavaScript, correct? So if you want to move away from that kind of a technology, it's not possible because you're stuck with it. You cannot move away, or you cannot just change the programming language like that. So that is where microservices would actually shine, and each of these components that you're building could be built in different languages, because at the end of the day, they're going to talk using simple HTTP like mechanisms. So you could probably build one component with a language like C Sharp, maybe another language or another component with C++, and but still these two services, these two components can talk with each other, right? So this is in a nutshell, like the fundamental philosophy behind microservices, like what microservices are all about. And now the other thing is, like I said, uh, there was this concept of service oriented architecture. And how are microservices different from service oriented architecture? Because in service oriented architectures also, it is the fundamental or the basic building block is a service, right? So how do they actually differ and all of that stuff? I will not get into the depths of what these what enterprise service bus are all about. And in a nutshell, I'll try to keep this part really simple. The fundamental difference is that other than the basic building block, which is the service itself, rest of them are totally different. So one thing in that is very common in SOA is centralized management. So whatever you're seeing, ESB, enterprise service bus, whatever you're looking at, so those ESBs are responsible for managing all the activities, and it orchestrates everything in between these services, which is fundamentally against the rule or against the principles of microservices. So except for the basic building block, everything else is actually separate or different in the case of microservices and service-oriented architectures. Now, let us take a look at uh, what characteristics, or for example, if you're building a services, if you're building a bunch of services, what characteristics would actually make them microservices? Let us take a look at that specific thing. So when I say componentization via services, so there is one primary thing which I would probably want to bring in here and reiterate. So you must have heard of these things called libraries, right? So if you're writing a C code, probably stdi standard io.h, so that's a header file you would include. And maybe if you want to do some additional functionality, maybe you would want to do some cryptography or anything, you would include new libraries, right? So and we are now talking of services. How services and libraries differ from each other is that, like in the case of a library, everything will happen in the same process. So everything happens in memory and everything is inside of the same process itself. But in the case of a service, everything happens outside of your current process. So there is a difference in the boundary there. So in the case of service, everything is outside of your process and outside of your process boundaries. Now, if you're building things in such a way that anything that is being done outside of your service or outside of your process boundary, and you're offloading something to a component which is outside of your process boundary, those are services. Now you're able to understand what services are. So services are those functionality which you build outside of your process, right? Now what this basically says is that you will have to break down your application, or you will have to build your components around services. Okay. And second thing is, if you are in a real world software development scenario, you are basically building a software product to solve a specific challenge. And the way you have to build your services that we are talking of, or the components that we are talking of, is that they have to serve a specific business capability. Say, for example, if you consider an e-commerce application like Amazon, right? So that specific application is could be broken down. In fact, Amazon uses microservices. So for example, if you place an order, it could be talking to say some order management service. If you are trying to check if your order has been shipped or not, maybe you're talking to a delivery service or a shipping service, and whatever payment that you make, right? So that specific logic may be residing inside of a payment service. So there could be multiple services which are built specifically for serving a specific business capability, and these functionalities actually work together. So, and then one other fundamental thing, or this is basically a mindset: products, not projects, right? So what that basically means is that generally when we talk of software, right? So when we talk of a project, so what you do is you build some code and you're done and dusted. But that's not exactly how the thing with microservices works. So you are going to build something, you're going to deliver it, you're going to make sure it is functional, you're going to support it when after it is deployed in production. So when we say production is nothing but something which is already delivered to the user. That environment is what we call production. So whatever you use, right, so that is basically production version of the system that you're using, correct? And there are several things that we need to actually ensure as a part of this. And it is always ever evolving. There is no point in the life cycle of your entire work where it says that yes, we are done with it. There is nothing like complete. There is always scope for improvement, and that is basically a product mentality. It's not like a project where it is done and we are going to move on with the next thing that's coming up. So there are several others, and few what I would want to highlight is the specific thing which is basically designed for failure. And like I said, microservices are a way of doing distributed computing, right? So whatever challenges you have with distributed computing, you're always taking them along with you in the case of microservices, right? So that is why microservices, even though they sound fancy and even though they sound they provide a lot of advantages, they also have their own uh, bottlenecks which could topple your entire product itself, right? And this evolutionary design is something that is a repercussion of this mindset that I'm talking of. So your design should always be in such a way that any incoming change, if you remember one challenge with the monolith that I have spoken of, that was basically that any new change that you're coming in, that could be very difficult to implement because your code does not let you do that because of some design decisions that you have taken at some point in time previously, right? So now what we should make sure is whatever design that we are coming up, however we are breaking this functionality into different services, that has to be able to cater to the evolutionary changes. So your product might evolve over a period of time, and that is where this evolutionary design thing actually comes into the picture. uh, there are other things that we can talk of, which is infrastructure automation. I'm not going to get into decentralized governance and decentralized data management. These would become evident as and when we move further. But infrastructure automation is something that I would want to stress. So if we look at how we deploy software, right? So software deployment is basically whenever you build an application. Say, for example, if you're building a C program, you would get a .object file, right? And then you would run or basically your .object file is what actually could be understood by your runtime or your compiler or whatever, correct? So similarly, when you actually build an application, you would have some sort of what do we say, build artifacts, or artifacts as we could call them. So that are a result of your entire application. Those artifacts are what you would deploy. So you could probably do it manually, and you could get an application up and running. But in the case of microservices, what we always try to make sure is this process of building and fetching your artifacts and then deploying them on your server that has to be automated. There should not be any manual intervention, because any manual intervention could lead to a lot of unforeseen circumstances which are supposed to be sort of avoided. And I mean, you could still run with manual interventions, but that would only limit your capabilities in how fast you can take a specific feature to your customer or end user. Right now, let us move further. What challenges? Like I said, yes, these are distributed. Microservices are a way to do distributed computing, right? So what actually would make them hard is that all the challenges that we have with distributed computing. And second thing is, when we are talking of what do we say, distributed computing and microservices in specific. So there was one point that I skipped, which is basically the data management, right? So in general, if you're building an application which is a monolith and it has a specific database it talks to, right? So there will be only one single data source, but that's not the case in the case of microservices. Each service that you build could have its own database. You could build a service in that way because you want your microservice to be as independent as possible and to be as fully functional as possible. So you would try to keep it in within the same service boundary, right? So that is where the concept of having one single database for one microservice actually comes into the picture. Now consider a use case of our e-commerce itself. Say you are ordering something on Amazon. Okay, so that order actually goes to that request actually goes to the order service. Now what order service should do is it should verify if there is enough inventory for you to place an order. So it might give a call to the inventory database, and inventory says, yes, I have enough inventory, and now your order should be created, right? So whatever your order that you're placing, it has to be created, and it should also initiate a payment, right? So payment, say now assume a case where each of these are dealing with their own databases, right? So now one database would have the information that yes, an order has been created, and payment confirmation might be within another database, and the shipping information could be in another database altogether. Now for one single order, if you look at it, there are, in a very trivial scenario, we are looking at 3 different databases where you have data in. Now it is always a challenging scenario if you have to keep the data in sync across all 3 databases, right? So that is where the data consistency problem actually comes into the picture, and there is a lot of activity, a lot of work that you need to do in order to achieve distributed transactions. If you generally, if you look at databases, we talk of transactions, right? So there are asset properties and all these. So these fundamentals would still should still be holding good, but they would hold good only if the transaction is happening inside of one database. So the atomicity, consistency, isolation, and durability that we have studied of, they would always hold good if you're working on one single database. But when you're talking of multiple databases and a distributed transaction across all these databases, your asset properties will not hold good. But how will you guarantee asset promise? So that is where the additional work that I'm talking of in order to achieve the data consistency would come into the picture. And yes, observability and making sure you have a real good picture with respect to what is happening inside your code is always a tough thing to solve. And also from an infrastructure standpoint, a lot of things have to be automated, and only that is when people will be able to move further or forward with a lot of conviction and a lot of velocity. So that is, these basically are things which would make microservices a hard thing and a tricky thing to do, right? So we are going to look at few patterns, and so far from the characteristics and all these stuff, we have understood in principle, or we have seen at least in principle, what microservices are all about, right? So but there are certain patterns which have emerged over a period of time. So probably I can give you a very rough understanding of what I mean by a pattern. Okay, so say you're trying to solve a particular problem and you have come up with a specific design in order to solve the problem, right? And also consider a case where someone else independent of you, like, no relation between like what you are doing and he is doing, but he is also trying to solve the same problem and he has come up with a solution. There would be a certain certain steps which would be taken. There would be a certain structure of the solutions that you guys have come up with. Now multiple people are coming up with a solution or with multiple solutions which could have same structure. Now the structure that has emerged out of all of these solutions, right? So that is a pattern. So pattern are or a pattern is nothing but a sort of a solution to a common problem, and that could solve that problem under a specific circumstance. So that is basically what patterns are, and patterns actually emerge over a period of time. And also probably, I mean, another example that I could maybe think of is, say for example, you are trying to solve minimum edit distance. It's a standard computer science problem, right? So if you're given two strings, how how different these two strings are. So what you would do is you would probably apply some dynamic programming technique, and that is a pattern that you're applying there. So patterns emerge over a period of time, and we are now going to look at what sort of patterns have emerged in the world of microservices. So there are different categories of patterns that we are going to, we have in microservices. So few of them, like I said, pattern is basically to solve a specific challenge. And so what decomposition patterns basically means is that if you have already an application which you have built like a monolith, like a traditional application, now to break this application down or to migrate from a monolith structure to a microservices structure, the kind of patterns that you would be applying would actually fall under the decomposition patterns and the integration patterns. So what integration patterns are all about is, assume that, okay, fine, you have figured out how to decompose or break down your application. Now how will you ensure that these services that you have built are talking to each other appropriately? That is where the integration patterns actually come into the picture. Okay, and what database patterns actually talk about is how your data has to be structured. What should your data architecture look like, right? So for different use cases, different scenarios, you would have different patterns, and they are classified under the database patterns. And similarly, observability. So observability is nothing but getting a view of the state of your application or your service at any point in time. So to achieve different kinds of observability metrics, we have different kinds of patterns that we could apply. And the final thing is the cross-cutting concerns patterns. So what are cross-cutting concerns? So now we have different services, right? But all these services could be requiring a certain functionality across all of them, and that functionality is common to all these services. So these kind of things which are common across all of your layers or all of your services, so those are cross-cutting concerns. So for example, logging. So uh, every service would require logging. And similarly, say authentication, right? So how would you authentication and authorization? So how would you authenticate and authorize a user, right? So that could be a common concern for all of these services. So how would you handle these kind of things which are common across all the services? So those are cross-cutting patterns. And we basically, I mean, I've listed down few decomposition patterns and database patterns, and we will look at them at a very high level. Let's not get into the depths of it, and I'll try to keep these very simple. So I mean, one specific thing that we had already looked at is decomposing something based on the business capability. I had given the example of like order management service, inventory service, payment service. So these are basically not just these services are not just built based on some intuition. We are actually looking at what sort of business capabilities or business verticals we have, and they are split based on those business capabilities, right? And we'll not go into, I mean, these are basically subdomain and strangler pattern are more like more deeper applications of whatever you have from a decomposition perspective. But they are again for challenge or addressing the same challenge. Like how could you better decompose your services so that your services are independent, your services are self-sustainable. When I say self-sustainable, whatever it needs to require or whatever it requires to do a job, it can do it by itself. It is not dependent on anything in or any other service or any other external factor. So it is to ensure that your services are built in such a way you have these decomposition patterns. And within the database patterns, I will talk of what command query responsibility segregation is, because this is something that we at Frequent use very heavily, and you'll be able to understand this further. But one thing that I would want to talk of is the Saga pattern. If you remember the use case that I had spoken of, where you're placing an order and different services have different databases into which you are actually putting data. Now, how would you ensure that all these data sources across are in sync? So that is where this Saga pattern actually comes into the picture. So Saga is nothing but you have a separate centralized, or it's not exactly centralized, but it is at the service level itself, right? So what you basically do is when you have a transaction that is spread that is involving multiple databases, so to ensure that we are keeping the data consistent across all the data sources, and we are also delivering on the asset guarantees that we have, right? So basically we create one centralized one common an orchestrator kind of a thing, if I can say so. That orchestrator will ensure that, okay, so consider this use case. So you have placed an order, and the order database has added an entry to the database saying the order is created. Okay, now you have triggered the payment service. The order service had triggered the payment service saying that, okay, initiate the payment. For whatever reasons, the payment had actually failed. But what you had done is you had already made an entry into your database saying that the order is created. Now, since the payment is failed, I should not say that the order is created. I should say that, I have to in fact get rid of that specific order created entry or order made entry from the order database. So there would be one like an object, if I have to put it in very, very simple terms. So there would be one specific object that would be responsible saying that, okay, there is a payment failure. So now what I will have to do is I'll have to go back and delete this entry from the database. So you have this supervising structure that you create around your distributed transaction, and that supervising construct is nothing but your Saga, as we call it. So this pattern that we use to ensure consistency and across a distributed transaction is nothing but a Saga. Okay, so we'll take a look at what CQRS, command query responsibility segregation, is all about. Okay, so now we have seen to some extent what microservices are all about, and what I mean so far whatever I've spoken of is more like microservices are being used by Amazon, and Netflix uses microservices, and in fact every large company you take, they're using some sort of distributed computing or the other, right? So should we start building applications in the same way because it is the next big thing, and it is going to because Google is able to serve 1 billion users using this kind of architectures. So are we going to should we start using this architectures? Not exactly. It basically depends on the kind of use case. Say for example, if you're building a simple student record management application or a library management system, so these kind of systems, they don't need microservices to work fine. So you would have a limited set of functionality that you're building, and if you have a limited user base that you're serving, and if the scope of your entire work is kind of limited, or if it is a minimum viable product, okay, so you're kind of trying to launch your first version to the market to see if the market is going to require the product, is going to use the product or not. So for these kind of scenarios, microservices could be an overkill, because you will have to deal with a lot of unnecessary complexity, and that only is going to pull you back and not going to take you forward. But in certain other use cases where your for example, our use case, the kind of users that we serve and the number of users that we serve, and the kind of complexity that we have. In fact, we have started as a monolith. So Prickvin's application has started as a monolith, and it has evolved to where we are currently. So so I mean, it depends on the kind of use case that you're going to start with. I don't at least suggest that you should start off building microservices. In fact, wherever possible, start building a monolith, and once you hit the limitations of dealing with a monolith, that is when you could probably start off exploring microservices. Because these services or the service boundaries that I'm talking of, which service is supposed to do what, if you're not going to get it right, you're heading towards a disaster. So to avoid such kind of things, and unless and until you have a real good picture with respect to what your boundaries are with respect to your business verticals, unless you have that, you're not it is not always suggested to move towards microservices, right? So I mean, that should be, I mean, the key takeaway, at least as a part of this entire discussion. So now let us move to our real world use case. So what was our application like? So to give you a context, the legacy application, or the way we have started off, is we had started off in 2003. So Prickwin had started off in 2003. And when Prickwin had started, it had started as a monolith. The entire architecture is residing inside of one single code base. You have a UI layer, a presentation layer, and the presentation layer is what the user interacts with. So we were using ASP.NET, classic ASP. In fact, back in 2003 when everything had started off, and then we had a business layer which was written using Visual Basic. So it was VB they were using as the backend, and we had a data access layer, and the database was Microsoft SQL Server that we were using, right? So there were two sides to this application. Okay, so there is one application where certain set of users are entering or adding data, and the other side is the read side, where this is the actual product which the end users use. Okay, so all the internal users will write to the database, and this data is actually pulled out or read from the database and shown on a different application. So this is the kind of setup with which we have started off. And what happened over a period of time was we kept adding more and more data. So when we add data to the database, so what happens is, when we talk of databases, you must all be aware of normalization, right? So why we use normalization is to keep the data as deduplicated as possible. You would try to avoid any kind of duplications, because these are relational databases. So there is a specific structure to the data that you would actually write to the database. And this structure that we have to this specific database, to keep these writes as less expensive as possible, you try to normalize. So when you normalize, you could probably write the data with as less number of writes as possible. So that is basically the what do we say, the normalization in a nutshell. Okay, so and when you normalize, basically what happens is you would have a lot of tables, and if you want to get an aggregated view, you would have to do a lot of joins, database joins. And generally when you actually write a database query which has a lot of joins, that's actually an expensive operation that you're doing on the database, right? So we have evolved, or we have grown to a point where certain queries that we are running on the databases are involving joins on tables, a really huge number of tables, right? And the response time of these queries are exceeding over a minute. So the query is taking 1 minute to entirely compute whatever we are trying to fetch. And if you are actually making a user, say the user has clicked a button to see some data, and if you are making the user wait for 1 minute to entirely fetch the data and show him whatever he is looking at, that's not a really good user experience, and your user is bound to move away. So that is where we had started off. I mean, that is where we have employed CQRS. So I had spoken of CQRS as a database pattern, right? So CQRS basically means command query responsibility segregation. Command is nothing but whatever writes you do to the database, right? So any like create, update and delete operations. So these are basically commands. Queries your read side. So we have split the read and write. What does that actually mean? So we are going to write to one database and we are going to read from another database. So we are not going to write and read from the same database. We have split them. And also we have split the entire monolith that we have into multiple services. So how did we do that? We use something called domain driven. That is another paradigm of programming and domain driven design in a nutshell. It's basically used in scenarios where your business logic is very complex. So if you model, basically if you understand what a class is, right? So when you start with object-oriented programming, people talk of like class as a real-world representation of your entire, whatever you see in the real world is modeled as a class, right? But if you actually take it a step further, and if you're trying to model a specific domain of business, so that is not exactly so easy to do, and that is those are the kind of scenarios where domain-driven design actually shines, right? And we have I spoke of two separate databases, right? We are going to read from database and write to a different database. Now we have to keep these two databases in sync, so from what we are writing and from what we are reading, right? Otherwise, what if I'm writing to something and I'm reading from something else? How will I be able to get the latest data from the read side of the database? That is where event sourcing actually comes into the picture, and eventually consistent read and write sources. So uh, if I write to one database and if I immediately read from the read database, I might not be able to see whatever latest change I've made, right? So this is where eventual consistency actually comes into the picture. And we have a reactive architecture for data sync. So the event sourcing that I'm talking of. So to keep the read source and the write source in sync. So that is basically a reactive thing wherein everything is dealt in terms of events. So any write that we do actually emits an event and that gets consumed by the read side, which updates the read side of things. So there is an architecture or a system in place to do this activity. Now, how does it look like? So it was looking like this, wherein we have three different layers, and these layers are talking to one single database, and everything is from one single source of truth. So how this has changed is like this. Um, yeah. So this is basically the current view. So the right side still remains the same. So this is, you can consider this more like a legacy application in itself. So this is also, this is also being moved to a different, view, but this is the right side of things, and that writes to this database. This is a SQL Server, Microsoft SQL Server that we use. And if you whatever you see on the right side is the read side, right? So this is the application that the end users actually use. So what we do is whatever writes we do, they are basically moved to Elasticsearch and Mongo. So when you talk of MongoDB, this is basically a NoSQL database. There is no specific structure to your data. So what is the advantage of using a NoSQL structure? The advantage is that your reads are very fast, because in the case of an RDBMS, you have normalization, and reading something from the database might involve database joins. So that will reduce your performance. But on the NoSQL side, there is no relation whatsoever. Everything is unstructured and your reads are faster. So, one other takeaway here could be that if you are using, if your application is a write intensive application, you do a lot of writes, this is probably the choice of your database should be some relational database. But if you are actually doing a lot of reads from your application or on your application, maybe we should think of employing or using a NoSQL database. So in our case, the NoSQL databases that we are using ended up being Elasticsearch and Mongo, and we have multiple services which are actually talking to these data sources. And the React, we are using the React JS on the front end. So the front end is separate, and we have multiple teams working on different services. So the now any change that could come in, it could probably impact only one single service and probably some part of the database. So that way we are also able to accommodate the evolving nature of the business. So I mean, if you could like take a look back at the different principles and the characteristics that I've spoken of, they would all fall in place with this structure. So these are aligned in terms of the business capabilities. Each of these service would do whatever portion of the business or whatever vertical of the business it deals with. So that way, I mean, this is still an evolving service. We are in the process of certain services in future may have a separate database. Currently, we have one database for all the services that they talk with. In future, we might be moving towards a specific structure where each service would have its own database. And I mean, in a really concise manner, this could be a journey, how your application could evolve into microservices. So it started off as a monolith. We have hit some roadblocks. We had come up with a different architecture altogether in order to solve those roadblocks. And this would keep evolving as and when new things come in. We might have to restructure a few things here and there, and that's a journey that we need to embark on. And there is no such thing as yes, this is done and dusted. So it's always an ever evolving thing. Software is basically a piece of art that is a living thing. It breathes basically. Like whenever you add some new code, it is growing. So that is the mindset that that we need to take forward if you are embarking on the journey of microservices. So yeah, so that is basically it from my end. So these are certain other references that we could look up to understand further or explore further. I mean, as a part of your journey with microservices and distributed computing and distributed systems. So that's all, folks, from my end, and probably we can open up for questions if you have anything.
That's really great, Sai. Elaborated about architecture, the challenges. You showed real-time use cases, everything. That's really fantastic. I request the participants can have interaction with the Sai for a few minutes, or you can ask your questions. You can post your questions to Sai, so that he can clarify here itself. Over to members, you can unmute yourself and. If anyone wants to talk, you can unmute yourself and you can ask a question. Sai.
Or if you have any questions at a later point in time, I'll drop an email, my email ID here. You can reach out on my email ID as well with anything that might come up at a later point in time when you explore further.
I think it's better you can leave your.
Yeah, so I'll do that. I'll probably do that. Drop my email ID in the chat here.
Yeah. Someone, so you can post your questions to that mail ID so that we can answer directly to you. So it's a great evening again having your talk, Sai, and I saw Dr. Badri is also here. Dr. Badri, you want to give any uh, word on this talk? He's the secretary for Computer Society, Vice at the section. So,
Yeah, good evening, everyone. Yeah, it is nice that today we have a talk on distributed systems and microservices. I think Mr. Sai has given a clear insight into microlithic architecture and microservices application architecture. I think he has given an insight into this, and definitely whatever the topics that were covered today as a part of this lecture, at least we can understand when we have to use the microservice architecture and how to decompose the applications into services. And he has covered about data consistency, implementing the queries, and few of the patterns like decomposition patterns, database per service pattern, etc. I think whoever will be participating, you can have an extension for this, because this is quite interesting topic. Like we can go through the API gateway patterns. Similarly, we can go through patterns like observability patterns and UI patterns, etc. And he has given a real-time use case also. I think Netflix, Amazon, and eBay, etc. These are the real-time use cases who are evolved from monolithic architecture to microservice architecture. Right? I think this gives a new direction for especially for the student members to concentrate, because I think Sai has also has done his graduation from MVGR. That is what I came to know from Dr. Satish. So in general, distributed systems will be there in the 4th year of undergraduate study, where the students will not much focus in practical aspect point of view, just they will study exam point of view. But really this is more useful when you go for industry. So this motivation given by the lecture from Sai, I think further the participants should extend it, and definitely this will be useful when we go for a real-time scenario. Thanks to Sai for his contribution through IEEE Computer Society for the professional community. Thank you, Sai, and thank you, Sadish.
thank you, Badri. Really, it's like, as you said, he's very interested in each and every course, and as I mentioned earlier, he's always very interested to learn new things. Always, he always keep on with the faculty members to learn new things, and he want to do new innovative ideas. He want to implement that's I think that interest made him like this. In industry also, in a short time, he reached the peaks of in that particular areas. I know his hard work and all in these areas. I appreciate Sai. You are the best in your field. I know that, and I really thank to you for accepting our invitation and giving this talk. And I really happy to see you like this. And my request is what we'll add you in our group, so that whenever people having any issues on these areas, and I know you are very interested on machine learning, artificial intelligence domain also. If someone having any challenges, they will come to you, and you can help them with that, with your ideas.
Absolutely, sir. Absolutely. So we'll be happy to jump in wherever needed, and looking forward for more interactions like this. Thank you
Thank
for
you.
your
Thank you,
thank you
Prince.
for the opportunity now.
I know you are busy with your schedules, but thanks for allocating time for this kind of volunteer services. So, with this note, I really thank all the participants whoever attended for this, and I thank the members of Computer Society of IEEE Vizag Bay section, the Badri Raj Garu, Sudhakar Garu, and other members, and my colleagues from my organization. and student members, all people. Really thanks for your patience listening, and I hope you enjoyed this talk. Like this, we are planned so many activities from this environment. So I request all people join regularly and have sessions like this, and you can interact with experts so that you can have a network. Whenever you have a good networks, definitely you will have a good opportunities also. So make use of all these opportunities and make your career better. With this note, I thank each and everyone, especially Sai and my members. So we are before leaving. We have a practice to take a photo with your wonderful faces and all. I request all the people, please, on your videos so that I will take a pic of group pic. I request all the members to on your videos. And thank you, thank you. I request once again Sai and Badrigar, please on. Thank you very much. Thank you, Sai. Thank you very much.
No problem, sir. Yeah.
I'm living here, and thank you each and every one.
Thanks, everybody. Bye bye.
Bye bye.